of, and then set those two sides equal to each other. So now, what do we know? Well, we know that heat flow, the total heat flow through an object, is just the rate of change. Is the rate at which energy is flowing through this object, because yeah, it's just the because when I have some amount of energy that flows through this object, it's going that's the definition of having heat flow, right? Um, so dq over dt we can also say is the total heat flow, and then where q is equal to the energy flowing into a system, into slash out of a system. Okay, so now what is energy? Well, we can write energy as, since we would want it to be in the form of some kind of triple integral, because then we can just set the inner functions equal to each other. So we can say that, let's first solve for q and then take the time derivative of q to get. So what we can do is we can say that q is just equal to the triple integral of q over v dv, right? So dq over dv, that would cause those to cancel, and this would just be q. Now I'll use a lowercase q. So there's a lowercase q for in here. So it's going to be dq over dv. Now the question is, what is dq over dv? Well, in order to do this, we're going to need some other things. Those other things we're going to need is the specific heat. So what is the specific heat? Specific heat is the relation, because we want to put this in terms of U, the temperature distribution. So how do we relate energy and temperature? Well, we know that the energy that goes into a system is going to be proportional to the change in temperature, right? It's going to be proportional to the change in temperature. If we input a huge amount of energy into a system, then the temperature is going to increase by a huge amount, right? And that proportionality might be different for Celsius or Fahrenheit. And then we also know that the greater the mass of the object, the less the temperature of the object will increase, given some finite amount of energy that we input. So we can also add mass into here. And the proportionality constant is called the specific heat. So Q, we can say, is equal to some proportionality constant times mass times the change in temperature. So, and then, yeah, and C is equal to the specific heat of material. So what can we also define? So what can we define specific heat as? What are the units for it? Well, so by definition, it's the proportionality between energy and temperature. And so what we get is, if we solve for C, we get that C is equal to Q divided by mass times change in temperature. And the units for this would be joules, right? Energy divided by kilograms times temperature, could be Kelvin, right? Degrees Kelvin. So the idea is that if this is so, then when we have 1 kilogram of this material, and we increase that material by 1 degree Celsius, then we can define C, specific heat, to be the energy required to do so. So we can define, the specific heat is defined to be the energy required, right? The energy required to increase materials, to increase 1 kilogram of a material by 1 degree Celsius, or if you're dealing in kelvins. So specific heat is the energy required to increase 1 kilogram of material by 1 degree Celsius. So now we know what specific heat is. And another thing that we'll be using is whoops, that's not the right thing. That's not is density. Density is just we write as the Greek letter rho. I think it's Greek, which equals density, which is equal to mass divided by volume. And the reason we would have that is because you'll see. So now we know that C is equal to Q divided by M times change in U. So specific heat is equal to energy that's put into the system divided by the mass times the change in temperature. And the idea is that, and what we're trying to solve for is what dQ or Q over V is, right? So what is Q over V? So what is Q over V, right? Well, the idea is that if we multiply C by mass, then those terms would cancel out. So if we take C, we multiply it by M, and then this would be equal to Q over the change in temperature, right? And then so if we wanted to solve for Q, we get that C times M times the change in temperature is equal to Q. But we also have to divide by V. And when we divide both sides by V, we can put the mass divided by volume together. And we will get that C times mass divided by volume is just the density of the material, times U is just the temperature distribution, times U will give us Q divided by V. And then essentially what we're going to do is we're just going to sum this up and across the entire material. So what we're going to do is we're going to take, we know that Q is equal to, I should probably have been using little q here, little q, and q. So we essentially just solve for Q over V, and we can rewrite it in terms of this, in terms of two numbers that specify about what type of material we're using, and we're multiplying it by the temperature distribution. But Q is going to be the triple integral of the what is called of the specific heat times the density times the temperature distribution, and then dV, which is dx, dy, dz. Right? Yeah, it's this right here. And then we now know what Q is. But remember, the total heat flow is the rate of change of temperature through this rate of change of energy through this object. So what we can do is we can say that dq over dt is going to be equal to the triple integral of the derivative with respect to time of C times density, specific heat times density times the temperature distribution, dx, dy, dz, which is equal to the total heat flow going in or out of flowing through the material we're using. And now we can finally make the equation. We can set this equal to this. So I'll circle this right here. And we finally get that the volume integral of the derivative with respect to time of C of specific heat times density times temperature distribution, dx, dy, dz, is equal to the volume integral of the divergence of the negative thermal conductivity times the gradient of the temperature distribution, dx, dy, dz. Okay, and another thing to point out, we actually did make a quick mistake here. What we actually want to solve for is negative dq dt. The reason for that is because if the energy that's flowing through the rate of change of energy that flows into if we have heat flow, and the heat flows out of the material, like here, maybe it flows out of the object, then we have a positive amount of heat flow. But if we had dq over dt, this is the rate of change of energy flowing through the system, or through the system. And this would say that a positive heat flow would be when heat is flowing into the system, right? Which is not what we want. We want a positive heat flow to be when heat is flowing out of the system, when we have heat flowing through the system. So, in other words, heat flows from hot to cold. So we have to make it negative. So we're solving for the negative value. We get this right here. And then we get both sides have negatives. And then since both sides have negatives, the negatives cancel out. And what we can do is we can set the inner functions equal to each other, since we're taking the same operation, right? If you input one something into a transformation, you input something else into a transformation, and they output the same thing, then the inputs have to be the same. If for every input there's one output, so these we can set equal to each other, and what we get is that the divergence. Sorry, this is positive because we brought the negative out to the outside. Right, we brought that negative out. So we get that the divergence of the thermal conductivity times the gradient of the temperature distribution is equal to the derivative with respect to time of the specific heat of the material times the density times the temperature distribution. Now the density, as time goes by, the density does not depend on time. The density only, in the normal case, would only depend on space. So we can bring the density out, right? To get that the divergence of thermal conductivity times the gradient of the temperature distribution is equal to the density. And I believe we should also be able to bring out the specific heat, because specific heat. Let's see, what is the definition of the specific heat? Is the energy required to increase 1 kilogram of the material by 1 degree Celsius, which should only depend on space it could change as the temperature changes, right? It could change as the temperature changes. So what we should get is this right here: density times the different temperature density times specific heat times the temperature distribution. So this is the generalized heat equation right here. Okay, but the thing is, it's commonly written that the thermal conductivity and the specific heat is constant for a relative range of temperatures. So this is the heat equation.